This is Sam's Science Channel, and the topic today is tomography or X-ray slice imaging. Let me start with X-rays. The idea with X-rays is that you can see through stuff. For example, this box of candy can be seen through, and immediately we see that Alexander and I ate half of the candy before starting the imaging. Well, talking of Alexander, it's this guy on the right. He built my X-ray lab at the University of Helsinki. And here is Zenit Purisha. She defended her PhD thesis a year and a half ago and now works at Aalto University. On my channel you can also see a video report of her PhD thesis defense. So this is the X-ray lab we have in Helsinki. Here's an X-ray camera. This is a Hello Kitty Easter egg, and behind Zenit there is an X-ray source. An X-ray imaging works like this. From the X-ray source, there are X-rays coming out, going through some object, and then recorded by the camera. And then we see an image like this, where you can see how much stuff there was on the way of the X-ray. So with these delicate petals, not so much stuff, but through the middle of the flower, there is more stuff. Of course, doctors use this technology all the time. They have been doing so for over 100 years. For example, you can see this nasty fracture in this poor patient's nose. So it's really good tool for doctors to see what's going on inside the patients. But today, actually the main topic is not this kind of traditional X-ray imaging, but slice imaging. So this is a slice image through a human head. You can see the eyes here. Here's the nose, the brain. The white one is skull bone. So how do you take an image like this? You can't do it by just putting something between the X-ray source and the camera. Rather, this image has to be constructed using a mathematical algorithm. Let me explain how. When the X-ray is traveling through the human head, it's getting weaker depending on what kind of tissue it's encountering. Then actually we can use a mathematical trick based on logarithm to make the ray actually measure how much stuff in total did it encounter on its way through the head. So this amount is something we can calculate out of the X-ray image we took using the logarithm. So if you ever think, where does anyone need a logarithm? This is one answer. In medical imaging, it's crucial. A basic idea in slice imaging is to collect a lot of these informations. So for example, with this kind of linear movement through the head, you collect such a profile of how much stuff was there through each of the X-ray traveling this direction. Then an important part of tomography is rotation. We collect the profile from all directions around the patient. This technology was first invented and implemented by Cormack and Hounsfield. This is Hounsfield's original device. You can see the linear movement part here and the rotation around the patient's head. And this is one of the original slice images recorded by Hounsfield. Also, let me note that the idea of reconstructing the image from these line integrals from all directions was already an old idea dating to 1917. This was Johann Radon's celebrated theorem, although Cormack and Hounsfield didn't know about it. So this is my message to all mathematicians. Please tell about your great ideas for a wide audience so that we can get life-saving technology into use faster. These days, tomography machines look something like this. Maybe you've seen these in Gray's Anatomy or the house, or maybe even in a hospital. So what happens here is that a 400 kilogram arrangement rotates there, having a very strong X-ray source and cameras. I'm glad they usually keep this lid closed, because as you can see, even the sheet is starting to move in the wind. So it's quite quite an energetic situation, this measurement. Now we arrive at the mathematical problem. It's an inverse problem. So we know all of these yellow profiles by measurement, and then the question is, what is the object that produces exactly this data? This is going from effect to cause. It's solving an inverse problem. And my goal today is to explain to you how does this work. This is the most usual reconstruction method for tomographic data. It's called filtered back projection, and you can see how it gradually builds back the image from the measurements. So after watching this video, you know what is happening here. One of the most important applications of tomographic imaging is detecting what kind of stroke does a patient have. Usually it's one of these two options. Here is an ischemic stroke where a blood clot is preventing blood from entering this part of the brain. This can be treated by blood thinning medication, but it should be started as soon as possible. If this situation remains for 4 hours or more, the part of the brain probably cannot be saved. This is the other type of stroke. It's hemorrhage, so there's a bleeding in the brain. Some blood vessel has ruptured and there's blood where there shouldn't be blood. Now, the three symptoms are exactly the same, but the treatment is very different. You should not give blood thinning medication to a bleeding patient. However, tomographic imaging is a lifesaver here because, as you can see, it's like night and day, the difference between these two conditions, and the doctors can continue with the right treatment. Next, we'll have a little test for you. We'll see if you are a natural tomographer. The idea is like this. So I'll demonstrate first with this very simple rectangle. So this is the data, and what this means is that for each number in this yellow graph is coded how long distance did the ray travel inside the white material. So all of these rays here give 0 because they only travel inside the black area. This one here goes a tiny bit inside the white, so there is a tiny number here. Whereas somewhere here is a ray that travels all the way here through the white, so there we actually record the maximum value like this. So that's how the measurement works. But of course, in tomography, in the inverse problem, this is what we have. So we see the data and we should find out what is inside. Warmed up already? Let's try. This is the first mystery object. You can see the data. What is inside? I will give you 3 options. It's one of these shapes, either a disc, a pentagon, or triangle. You can go back in the video and watch the data again and see if you can figure out which one is the correct one. I will reveal it now. The answer is triangle. As you can see from here, if you stop the video at any point, you can check that the yellow curve records how long way did the ray travel inside the white area. Okay, let's go to a more difficult one. This is a written character, not from the Western alphabet though. This is a Chinese character. It's one of these. It's either 3 or river or rice paddy. So I encourage you to go back a little bit in the video, watch the data again, and try to deduce which one of these produced the data. And now I'll go to the solution, which is river. And maybe one of the main directions is to look, how does it look directly vertical, so you can see that in that situation there are the longest possible routes for X-rays to travel inside the white material. Okay, getting harder. This is one of the characters in the Western alphabet. But which one is it? It is either S, B, or W. Can you guess what it is? Please check back with the data a little bit, think about it, and come up with your answer. Remember to look carefully about the vertical X-rays. They will reveal something about the character. But now let's go forward, and you will see that it's B. It's rather complicated already, with the B having holes and all, so it's a bit difficult already, except that there's a hint. You see, it's Batman. This again is a character, but don't rush to conclusions. Watch the data. Think about the vertical ones. What might it be? What might it be? It is one of these. E up, regular E, or E backwards, or exists, as we mathematicians say. Check back with the data, think about it, and you'll solve it. It's this one. Exists. And you can see it from the vertical one, because on this side you have longer roots inside the white area instead of on this side. So with the regular E, you would have this thing here on the left side instead of right. And then we'll go to more difficult ones. Namely, this is not only black and white. This written character also has grayscales in it. What could it be? Well, it is one of these emojis. Either poop, or smiley face, or unicorn. What could it be? Check back with the data, think about it. It's really hard though, so I will reveal the solution now. It is unicorn. And maybe the only way to realize what it is maybe some direction like this, where you can see the horn of the unicorn making a shape here. But really it's not very obvious, I would say. It's really hard. And now we get to the final and most difficult mystery of all. This is a medical one, not a written character anymore. What could it be? At least to me it looks pretty incomprehensible. It's one of these. It's either ischemic stroke, hemorrhage, or a rare but serious condition called unicornism. Well, you might already get a hang of my sense of humor, so actually it is unicornism. And at this point I would say that of course these three options do not make any sense. In practice there is something inside the scanner, we get some data, we don't get any three choices. The machine has to compute what is there. So we need some method that takes as input the measurement, uses it in some way, and calculates back whatever there is. And next I will explain to you how does the most popular reconstruction method work. So I'll show first the data of this very simple target of two disks. You can see the two disk forms moving over each other in the data. Of course, the inverse problem is this one. So we only know the data, and somehow we should find back what is the object causing this data. So the first trick here is the back projection. The back projection means that we throw our measurement data back into the image domain. So the yellow curve is our data, and we know the direction where it came from. In this case, horizontally. So for example, here we have 0. So we throw 0, which is black color, back into the image. Here, which is the largest value, it's white. So we send white back to the image, and here medium value is medium gray. So we kind of take the whole form of this one and we just throw it back along the X-rays. And then we do this along several directions. For example, these. So here are 7 directions, and already you start to see the original target. Here the bigger disk, here the smaller one. Of course there are these weird triangle thingies and so on. However, the main thing is already a bit visible. And now of course we can take all directions into account, not only 7. So we can go over all the half circle we measured, and you can see that we get quite nicely back the original target, but not quite. So the target is supposed to have only black and white color. However, this one has also these gray colors here. It's kind of blurred. How can we remove this blurring from the back projected image? Well, that's the filter. The filter works like this. We move from the image domain to the so-called frequency domain by using the Fourier transform, or FFT for fast Fourier transform. This picture is rather unintuitive for the human mind, but the idea there is that in the middle are large structures, slowly changing structures in the image, and on the boundary, edges and sharp features are coded into. Multiplication with ice cream cone, well, it just means that we multiply with the Fourier plane variable, the length. What this means is that if we think what happens to this small value, almost black value here, we multiply it by the distance from here to the center. So we see that it becomes a bit lighter color. After this multiplication thing, we do the inverse transform, and then we get the original target back. And actually, this here is the content of Johann Radon's famous mathematical theorem from 1917. Back projection followed by this filter gives you back the original object. Now, this filter may be a bit hard to visualize what it's doing, so let me show what happens when we apply it to a photograph. This is me in the Tokyo airport in Narita, my favorite shop, the Hello Kitty shop. And now if we apply the same filter to this image, we get this. All the edges and boundaries are greatly enhanced, so it's a kind of an edge enhancement filter. And now, getting back to the reconstruction of the human head slice, here I have combined both the back projection and filter into the same process, and that's how it works. Now you know. Thanks for watching. Remember to subscribe, and you're welcome to see more videos on Sam's Science channel.